attendees are in listen-only mode.
Okay, it's all yours, Howard.
Okay. Good morning from sunny Hawaii. This is Howard Wigg, Energy Analyst with the State Energy Office, and I am joined for this webinar on IECC 2015 by Eric Makala, who is in Boise, Idaho at the moment, and Eric is our consultant for the 2015 IECC. Just to introduce Eric, he is a very tall presence in the energy code world nationwide. He and I were recently at an energy code hearing in Louisville, Kentucky, and there were many proposals coming up for the 2018 IECC, and it was probably my imagination, but I think Eric was probably up at the mic testifying on behalf of one organization or another, probably at least one out of every 5 opportunities. That's how sought after he is, and also he's done energy code work, or is doing, for Bahrain and I believe it's Dubai in the Mideast, slightly different climate zone from Hawaii. And speaking of climate zones, he's also done energy code work in Fiji and in Saipan. So he's literally been all over the globe in literally all different climate zones. So we're very fortunate to have Eric with us. Myself, Howard Wigg, I have been working on codes almost since their inception, many years ago, and my specialty has been adapting the model or mainland code to Hawaii's conditions. And a couple years ago at a 2015 IECC hearing, we were fortunate to be able to create another climate zone, the tropical climate zone, which applies specifically to Hawaii. So we've been able to especially adapt the residential section as an option. You have a whole separate tropical design there. In this session on commercial buildings, the HVAC portion, we don't have many specific tropical amendments, but I will be covering at least one of them. And my specialty has been cool walls, where we're all familiar with the fact that reflective roofs are now required in climate zones 1, 2, 3, and in Hawaii for flat roofs, because they work so well. And I was asking myself for years, why not have cool walls? And that is in development. I'm working with other organizations, and we do have, as we saw yesterday in the envelope section, a cool wall provision. Anyway, not enough about me. If we could have the next slide, Eric.
Okay. I'll go ahead and grab this one, Howard.
Okay.
So as Howard said, I'm Eric Makala out of Boise, Idaho, and I'm a senior associate with Cadmus Group. And what we've tried to do in working with Howard and the State Energy Office is really to try to tailor the energy code as much as possible to the state of Hawaii, based on what we've learned in working in other tropical areas. So this was done with modeling, using Energy Plus models and things like that to really see what the biggest bang for the buck was and what made the most sense. And you're going to kind of see when we talk today about on the mechanical side, you're going to see some of the provisions we put in that are Hawaii specific. And what we found on the commercial side is, especially on the mechanical, there's a lot of things that do apply to your current methods of construction for commercial construction in Hawaii. So we'll take a look at those. But before we do that, I wanted to say that we are going to be taking questions in the webinar, and our goal today is to get through the material over this next hour, and then after that we'll go ahead and answer all the questions at one time. So if you've downloaded the slides for this webinar, you don't have this particular slide, and what we're going to ask you to do is actually email in your questions to the email address that's on your screen. It's jolyn.green at cadmusgroup.com. And I'll leave this up for a little bit longer so you can go ahead and write this down. And again, we'll go ahead and take all questions at the end of the webinar once we kind of accumulated everything. So I'll also have the slide up at the very end too. So if you don't have it written down, or something happens to your email address, definitely feel free to wait till the end, and this will bring us up again, so you can go ahead and send the email and questions into Howard and I for us to answer at the end of the session. So with that, I'm going to turn this back to you, Howard, and we'll get going. So.
Okay, and we do love questions. The more questions, the merrier. We are on this webinar to serve you, and we love it when we have a whole bunch of questions to answer. So by way of background, how did we evolve to IECC 2015? Well, one short answer is not nearly as quickly as we wanted to. In 2007, the Hawaii State Legislature created the Hawaii Building Code Council, and that is a statewide group. We meet once a month, and the Neighbor Island Building Division managers fly into Honolulu, and we sit around the same table and talk about the fire code, the seismic code, the electrical code, and so forth. And I chair the Energy Code Subcommittee. And when this council was formed, there was supposed to be funding. However, there was no funding, and in all the subsequent years, likewise, there has been zero funding, and as you can imagine, that has slowed us down just a little bit. We are still on the 2006 IECC, which is now a real dinosaur of a code, and many of designers, and probably most people in this audience, are already designing to 2015 or something very close to that. The outfit Hawaii Energy did a survey of the production residential builders in the Ewa Plains and found that they were designing homes about 30% more efficient than would have been the case with 2006, and that's just about the level of improvement that we made between 2006 and 2015. So fortunately, people are not stuck back there, and we were supposed to have gone from 2006 to 2009 to 2012, now to 15, and that is true of all the codes. Why do codes change so much? Answer: Moore's Law. You will recall that one of the founders of Intel Corporation looked at the progress of computers way back in 1971 and said, this technology is going to double in capacity and go half in size every 2 years. And if you think about it, that is truly, truly exponential growth. And he was pretty well on the money. One of the WAGs at Intel Corporation recently calculated that if a 1971 Volkswagen Beetle had gone through the same improvements, it could go 200,000 miles an hour, get 3 million miles to the gallon, and cost 4 cents. For those of you who have smartwatches on your wrist, you have more computing capability than did the entire U.S. military during the Korean War. That is Moore's Law in its essence, and the other building technologies have certainly not improved at that exponential rate, but they have improved dramatically. That's a good part of my job, is keeping track of those improvements and making sure that they're in the latest iteration of the energy codes. The best example of building technology improvement is LED lamps. They are just growing by leaps and bounds. The productivity, the efficiency is going up, the cost is coming down. And one of the sad things about not having updated the code is our high rises in Kaka'ako, which most of you are familiar with. You look at them and they look like they're entirely glass. Now, of course, they're not entirely glass. You have to hold the building up with something. But I really wonder, oh, and they have no overhangs whatsoever, totally exposed to the sun. And I just wonder about the performance of those buildings there. Had the new code been in place, there would have been a whole lot less glass there, or if there was a glass, there would have been a lot of trade-off in the form of super efficient equipment. Okay, enough of that. Let's go to the next slide, Eric. Structure. Structure is important in anything, and all codes, fire codes, electrical, and so forth, they're all structured this way. You have to start with scope and administration. What is this code covering? And you have to draw boundaries around that, what it doesn't cover, and then who administers it and how does the administration take place. Then, of course, definitions. If you've ever talked to lawyers or listened to lawyers, you see that they have their own vocabulary, and likewise doctors have their own vocabulary, and building code officials and building designers have their own vocabulary, sometimes with specialized meanings. So that's what the definition section is all about. Then comes general requirements, and most of those pages are occupied by defining the climate zones in every county in America. Fortunately, Hawaii just has one climate zone. We used to be with Southern Florida, Climate Zone 1. Now I am proud to report that this section begins with the new tropical climate zone, which boils down to being essentially Hawaii. And then we have the meat and potatoes of the code, and these are all the technical requirements. And then existing buildings. This is something that is new. The previous codes did cover existing buildings, but now they've been moved into their own separate section, and most of the questions that we have been getting regard existing buildings and specifically roof replacements. That's not covered in today's code, but that's a subject of great interest. And then finally referenced or standards, and a lot of the verbiage in the technical portion refers to other standards, and those standards are defined. And incidentally, although this is the IECC, ASHRAE also has its energy code 90.1, and the 90.1 or 2013 ASHRAE code is very approximately equal to 2015 IECC, so much so that they can be interchanged. Oh, and then other codes are beyond codes. This is a minimum, and the beyond codes generally improve the efficiency of the code by about 10%. They're not used a whole heck of a lot, but they do exist. Next slide, please. Energy savings. One of the best ways of reducing energy use is via compliance with the energy codes. If you look at those numbers on the orange setting on the right, 4,703 gigawatt hours. What is a gigawatt hour? It can power about 200,000 homes for a year. That is one heck of a lot of energy. We're talking over a 20-year period about saving, literally in little old Hawaii, well over $1 billion. And when you apply that nationwide, which is why Eric and I go to the national hearings, that savings number is multiplied many fold. Some analysts say that energy codes are the most effective technically effective and cost-effective way of reducing energy use. You're probably aware that something like 200 coal plants have been shut down, and usually they're the dirtiest coal plants on the mainland. And a big reason for that is the energy compliance with energy codes. Of course, that equals cleaner air. And in Hawaii, we have the Hawaii Clean Energy Initiative, which states that by the year 2045, 100% of our electrical production shall be from clean sources. And that is a combination of energy efficiency, reducing the consumption of electricity, plus the onset of the green or clean energy sources, the also photovoltaic panels all over the place. Hawaii is a leader in photovoltaic panels. So tremendous savings at really in a cost-effective way. Next slide, please.
Actually, Howard, can I interject something? It's something I didn't do at the very beginning, but our audience knows who we are, but we don't know who they are. So
good point.
I'm going to go ahead, and what I want to do is take a poll to find out who's out there and who's on this webinar. So I'm going to go ahead and launch the poll, and if you can pick the profession that most closely reflects who you are, that would be great. If you don't see something that looks like who you are, then you fall underneath the other category. But I'm going to go ahead and launch this now, and if you can take a minute and just let us know who you are out there. So go ahead and answer this, and we'll give you about a minute, and then we'll shut this down and we'll move on. Of course, I may not have to give you a minute because it looks like everything's stabilizing out pretty quickly. All right, it looks like everything's stable. I'm going to go ahead and close this now, and I will quickly share the results. And you can see it looks like the majority of the attendees are engineers, which is great because this is mechanical. We have quite a few architects, which is really nice to see. Only 12% other, which is normally other is our largest category. So, and about 15% plan review and inspection staff and building officials. So it's a great mix. So anyway, thank you very much for letting us do this. Now let's continue on, and we'll get you back to where we started. So. For some reason, hold on. For some reason, we just bounced to the end. Let me get us back to the slide that we're.
Okay. Yeah, we want to be on commercial provisions.
Yes, yeah. For some reason, it bounced me off. Okay, there we go. We're set.
And Eric, that preponderance of engineers means when you get into the meat and potatoes of this, you can be just as geeky as you want.
I don't know what to say, Howard. So go ahead.
So HVAC is a pretty geeky subject to begin with. So commercial provisions and overview, as most of you are aware, the commercial building section starts with the envelope, then goes to HVAC, then lighting, electrical. And why do we start with the envelope? Because it's a big determinant of the sizing and distribution of your HVAC section. The better the envelope is at keeping Hawaii's solar heat out, the smaller the sizing of the HVAC system is. And what is a commercial building? It is 3 floors, or above 3 floors, 4 floors and above. The determinant there is that 4 floors by law need to have an elevator. We are considering adding a new section called multifamily, and that would cover everything from the smaller apartment buildings up to the high-rises, such as we're seeing going up in Kaka'ako, because they as you well know, have very special needs. For instance, a lot of hot water needs. How are you going to take care of that? So next slide, please. General, this is the beginning part of the code, the scope and administration. And let's jump right to the next one there.
Okay.
Scope and application. So as I was mentioning before, ASHRAE 2013 is equivalent to IECC 2015, and some people prefer to follow that path, and that's fine. And then we have prescriptive versus performance for the IECC. Prescriptive, of course, is the code tells you what to do. I've heard many builders say, don't tell me how to build a building, just tell me what to do. And that's that. It's very specific in the requirements. You must have a SEER rating of X, and your ducting must be Y, and so forth. And then you've got the good old performance section, and that would apply when you want to do something very unique with your building, but you know you've got to comply with the energy code even by deviating from the prescriptive path. So what you do is model the potential energy consumption of your building given the prescriptive path, and then you do what you want to do, but in the end you have to model the energy consumption and prove to the plan checker that your consumption is either equal to or less than would be the case with the prescriptive code, prescriptive path. But most people choose to follow the prescriptive. So with that, Eric, let me turn it over to you. Building mechanical systems.
Great, thank you, Howard. So as Howard defined what a commercial building was, and also what a high-rise residential is, and essentially what we're going to be covering over the next bit, we'll focus on mechanical systems that provide cooling and also ventilation to these systems, and we're also going to be looking at requirements, new requirements for parking garage ventilation systems, things that we're not going to be covering in this session, but it's worthwhile getting a copy of the energy code to take a look at. There's new requirements in the code for walk-in coolers, walk-in freezers, refrigerated warehouse coolers, and refrigerated warehouse freezers, specifically focused on the shell and also on the systems that serve that. So these are new requirements that have never been in the code. We also have requirements that deal with kitchen exhaust, large kitchen exhaust hoods too. And again, we're not, in the interest of time, we're not going to be able to cover that today. But those of you that are familiar with ASHRAE 90.1, either 2010 or 2013, are going to notice a lot of similarities when it comes to mechanical requirements between the ASHRAE standard and the 2015 version of the IECC. And the reason that this is essentially ASHRAE participates in the IECC code development process and brings with it a lot of requirements out of the current ASHRAE standard 90.1. This includes equipment efficiency requirements, control requirements, and that type of thing. So on the mechanical, you'll see the requirements are very, very similar. And if you're used to using ASHRAE right now, then there's not going to be a lot of changes because the requirements have been pretty much brought over verbatim. I mean, everything is there, numbers are there, thresholds are there, and things like that. The systems we're going to be looking at, again, are systems that basically provide space conditioning for the old code used to say human occupancy. We don't use that term anymore, but it's space conditioning for the building to make sure that our occupants are as comfortable as they possibly can be in those buildings. So we're going to be kind of not going through everything, but going through kind of some of the highlights that are in the mechanical requirements. One of the first requirement that's currently in your 2006 code and has been in code, every code after that, is essentially making sure your system is sized properly to meet the demands of the building. And Howard mentioned the fact that we're now requiring that the building envelope be more efficient. better windows, actually continuous air barriers to reduce infiltration loads. So we have reduced solar heat gain coefficient requirements in the windows. We have cool roof requirements on the roofs for flat roofs. All of these will reduce our cooling loads pretty significantly, and they have to be reflected in the load calculations. In addition, we've significantly reduced the lighting power density in the inside, so our internal loads have also been reduced too, and we're requiring more daylighting. So throughout the day, lights will either be in a dimmed or off mode based on what's going on outside, obviously. But all of these will impact the load calculations. And so the nice thing about this code is there's actually a rate of return. If I invest in my building shell, if I invest and put in a good lighting system, for one thing, you're going to get good energy savings. So reduction in the cost to operate the building, and you can start making your system smaller. And I know there's a certain threshold you can get down to typically before you feel uncomfortable, because you want to make sure you have a safety factor for your mechanical systems. But what we've seen over time is mechanical systems have shrank because of better efficiencies. So the equipment sizing requirement basically now requires either ASHRAE or ANSI ASHRAE ACA 183 or another approved equivalent method to size your cooling systems so that it actually is sized for the building. And then you need to make sure that you actually select a piece of equipment that meets the efficiency requirements, the current efficiency requirements that are in the code. And so these tables have been updated. The minimum efficiency requirements have been updated. Some of these are updated because the federal government, under the National Appliance Energy Conservation Act, essentially said that you cannot manufacture and sell equipment that doesn't meet minimum requirements in the code. And those, what we call NACA minimums, are reflected in the equipment efficiency tables. This is just one of the many tables, but it deals, in your case, with just about any type of cooling equipment that you can think of, all the way from single zone packaged air conditioners all the way up to large chillers, so and cooling towers. So it reflects just about every type of equipment that you can think of and so all of that equipment has to meet minimum requirements, and sometimes the requirements will have both full load and part load efficiency requirements, and if that's the case, the piece of equipment has to meet both of those requirements. So again, the best thing to do is to get a copy of the code and look at the new efficiency requirements to make sure that what you're speccing actually meet or exceeds what's in the code.
Eric?
Yes, Howard.
Eric, yeah. Let me jump in to the envelope and AC sizing issue. Just on a very simple residential level, the old rule of thumb for a 2,000 square foot single-family home used to be 5 tons. There is one builder out on the Upper Plains who has built his envelope so tightly and used reflective surfaces that he cools a 2,000 square foot home with 2 tons. That's 1 ton per 1,000 square feet. And he uses this as a marketing tool to assure the would-be buyer that their monthly utility bill is going to be really, really low because of this, and the homes are totally, totally comfortable. That's the potential effect of a really good envelope and sizing your HVAC accordingly.
Great. Okay. So it does have a big impact then. So there are, there's obviously a lot of rule of thumbs out there that we used to have. The rule of thumb was 400 square feet per ton of cooling, and that number obviously goes up and down based on internal loads and amount of glass and that type of thing. So and the only way you really truly know that your system is sized properly is to do a load calculation, just to make sure it's actually, because you might actually be you might actually be at 300 square feet per ton, but you don't know it until you actually size the system. So the goal is to size the system for what's going on in that particular building. And there's no thresholds on how large your system or how small your system can be. It just says size it, do the load calculations, and select the piece of equipment that best reflects those load calculations. So So we've sized the system. We've selected the system with the best with the proper equipment efficiency to meet that. Now we need to make sure it has controls put on, and really the control requirements between the 2006 and 2015 have not changed that much. The goal with controls, especially for larger systems, is to make sure that when we size our cooling systems, we always size for worst case conditions. So it's going to be, we're trying to maintain a temperature of say 75 degrees on the inside. It's the hottest day possible on the outside. The building's fully loaded with people. All the lights are turned on. We have all the equipment turned on, and that's worst case. But when you actually look at the way the system operates, it doesn't hit worst case. It has to deal with worst case loads a lot of the time. So we want our systems to be able to run as efficiently as possible at part loads. So when we especially start getting into large chillers, there will be a lot of control requirements to make sure that the capacity of the system actually matches what's going on in the building. For a lot of the systems that are going in right now, they seem to be a lot of single zone unitary types of systems, package air conditioners. And so the single zone systems, the control requirements on those are fairly simple and almost look like a residential scale type of control. The first one is making sure that you have a thermostatic control. If you have humidity controls, you need to be able to control the humidity. Off-hour controls are important because if your system is if your building space is only going to be occupied from 8 in the morning until 6 o'clock at night, for example, there's no reason to have your system running full blast from the time your business shuts down until the next morning. So it's best to set the system up to be able to operate it at a higher temperature, and you'll save energy that way. And you're probably already doing this right now. So setback controls are required on all systems. So this is kind of the key thing. So you have to have a control. It's got to be a setback. And then if you downloaded the presentation before this, I've added a slide because I thought we should also talk about the requirement for an optimum start control. And essentially, most systems right now are designed to come on at the same time every day to get the system basically down to temperature. So if your occupancy is at 8 in the morning, and let's say you have your system designed to come on at 6 o'clock every morning to cool the temperature before the first occupant comes in. What this control will essentially do is to say, it'll look at the outside weather conditions, look at the interior temperatures, and it will optimize that start time. So maybe it only has to start an hour prior to occupancy to get it down to the temperature you want it to for the occupant. So if I can actually reduce my startup time, I'm going to be saving quite a bit of energy from that standpoint. So a new requirement again in the code, it's the optimum start. And this again is an ASHRAE. ASHRAE has the identical requirement because this requirement came from ASHRAE. Howard, why don't you talk about the new amendment for door switches?
I would be delighted. As we're all aware, Hawaii hotels have lanais, and you enter and exit the lanai through a large sliding glass door. And the occupant of the room, a tourist, very often, if they're allowed to do so, will open the lanai door, go out onto the lanai, and enjoy the great outdoors with the lanai door wide open. I don't have to tell you about the heat exchange consequences of that. We are cooling the great outdoors that way. So we have this Hawaii-specific provision that says that if a lanai door is open for more than 5 minutes, the air handler in the room shuts off and goes to default of 90 degrees F. Makes all kinds of sense, as studies have shown that the per room energy savings is pretty darned tremendous. And we expanded this not just to hotels, but to timeshare units, because we're all aware that some hotels are converting to timeshare, much to the discomfiture of the unions. And we've extended that to condominiums and guest suites as well. So a very simple measure, very Hawaii specific, and very, very effective in terms of saving energy. That's that.
Great, thank you, Howard. And I did notice that when Howard and I did a training training swing through the islands in November, and I noticed that a lot of the hotels that we stayed at actually they were already doing this. So this could actually be current practice in some cases. So, but it does make a lot of sense to do this. So, all right. Demand controlled ventilation. If you have a space, a building that actually requires a significant amount of outdoor air for ventilation loads, essentially what we're doing right now is that we're bringing in a lot of outdoor air, we're cooling that outdoor air, and then we're exhausting that outdoor air. And so what this is essentially saying is if we have a very high outdoor air load for, so let's say a health club, for example, maybe a health club will bring in quite a bit of outdoor air to make sure there's a lot of ventilation air in that space. That we need to be able to capture the energy loss. So instead of dumping this outdoor air to the great outdoors, it basically has to go through a heat exchanger system to capture the cool of that air, so that when we bring air into the space, we can actually pre-cool that air before it hits the cooling system. So this is demand control ventilation. This has actually been in the code for a few cycles. I can't remember if it's in the 2006 or not. It's an ASHRAE 2. So the threshold for this is if you have a space greater than 500 square feet with an average occupant load of about 25 people per 1,000 square feet of floor area, you are required to have this type of system. And the key, again, is to be able to, for demand control ventilation, you want to be able to modulate the ventilation air, because if the space, I'm going to take a church sanctuary, for example. Let's say on Sunday the church is packed. You're providing cool air in there. You're providing ventilation air in that space. But during the rest of the week, no one's using the sanctuary. There's no reason to bring in that much fresh air into that space. So you need a sensor that essentially can determine when that system should come on and at what rate that system should come on. So you're matching the ventilation coming into that space with the space that's the number of people in the space. So demand control ventilation, again, it's a very effective way of basically reducing ventilation air when it's not needed in that space, and that could be quite a bit of the time. What's different in this code provision, and I moved a slide. This just kind of talks about the efficiency of the energy recovery ventilation system. It has to be at least 50% efficiency. I know that some of the above code programs right now are speccing about a 70% efficient energy recovery ventilation system. So 50%, again, this is a minimum baseline code, but certainly you can get more efficient systems than 50%. But from a threshold standpoint, and that your next slide is probably going to be on enclosed parking garages, but I shifted that to the end of the ventilation requirements. That used to be in the earlier codes that essentially said that you had a threshold for CFM of fan system and outside air, and if you exceeded both of those, then you had to put a energy recovery ventilation system on this. The new code requirement is based on how the number of operating hours a ventilation system is operating per year. And this, from a code enforcement standpoint, might be a little bit tricky, because this is a question you're going to have to ask to the designer of how often is the space going to be occupied, what's the intent behind the space, and you need to do a sanity check to look at the building and kind of look at the answer and say, okay, does this match up? Obviously, if you have a church, for example, then you can assume that the space is going to be occupied at least one day a week, maybe more, but it's at least one day a week. So they actually might operate less than 8,000 hours per year. But if you have a building that is either 24 hours a day operation or standard occupancy load, maybe it's open for 10 hours a day, you know that it's going to be providing ventilation air for probably more than 8,000 hours a year. So the way this table works is you have how much outside air you're planning on bringing in, and then you have your design supply airflow. And if I'm only bringing in, if my system is operating less than 8,000 hours a year, for example, and let's say I'm bringing in 20% outside air, I would have to, in order for me to have to comply with this, my fan system would have to be at least 16,000 CFM. So it's a fairly large fan system. But the more outside air I'm bringing in, for example, if I'm at above 60,000 or 60% outside air, then my design supply airflow is going to be about 2,000 CFM, and anything above that, I need to provide energy recovery ventilation on that. If I
Eric,
Go ahead, sure.
oh, yeah, let me jump in with a little anecdote here. This doesn't regard the habitable space, but a parking garage, and this was Austin, Texas. And unlike Hawaii's garages, which are ventilated by the trade winds, this was a pretty well enclosed multi-story parking garage. And we were given a tour of this, and the proprietor was touting the tremendous energy savings that he had achieved. And I took him aside after a while and said, now, how did you get those savings? And it turned out that the garage is ventilated by huge, huge fans, and they were running 24/7, and they figured out that the garage, this is a municipal lot for workers and for entertainment venues, the garage was not occupied 24/7, but only a small fraction of that. And when the occupancy went way down, they would funnel the fans back down to about 10% load. And then when it was fully occupied, they'd ramp it up to 100% load. And this was the huge bulk of all of the energy savings that they were talking about in this facility. So good example of controlling fan speeds.
And actually, Howard, we have a requirement for you in the code, so that'll just do the same thing. So just it's in 2 slides, and we'll talk about that. So
okay.
That's okay. It was a perfect lead-in. So yeah, we'll handle that one in 2 slides. So you just kind of set me up on this one. So.
Okay.
So if I have a building that's operating, or a ventilation system operating more than 8,000 hours per year, you can see now that even for 10 to 20% outside air, the very first column, their fan system, if you have a fan system greater than or equal to 2,500 CFM, you're going to be required to have energy recovery ventilation. So in the hotter, humid climate zones, it actually makes sense, because not only are you're cooling down the air, but you're also dehumidifying that air too. And so there's a significant amount of energy savings on here. And obviously, the higher your outside air for buildings that operate pretty much year round, you will always have to have energy recovery ventilation. So when you start looking at 50% to 60% outside air, that greater than 0 means that any fan system you put on there, any supply air fan system will actually have to have an energy recovery ventilation. So when we're starting to bring in high amounts of ventilation air into the particular building. So, the interesting thing from a cost effectiveness standpoint too, because these values came from ASHRAE. ASHRAE does a cost effectiveness analysis, and they really try not to put anything in the code that they feel is not cost effective. So because this came right out of ASHRAE standard 90.1, it's in all climate zones. You can see actually these are all hot, humid climates, 1A through 6A. Well, actually they're not all hot, but they're all have high moisture content. Climate zone A, as in the tropical zone, is more humidity. They have been shown to be cost effective across these climate zones. So anyway, that's why it's in the code, and it makes sense. So now, Howard, let's get into your requirement for Austin. And so for Austin, actually, you are we're bringing in the same requirement into Hawaii that Austin has. This again is I think the key thing that Howard hit on is how you typically ventilate your parking garages through the trade winds. And this is specifically for enclosed parking garages, where you actually are bringing in mechanical ventilation air to make sure you're creating a healthy environment for the occupants in that space. And so the key thing is that you're reducing the amount of ventilation air in those parking garages when it's not needed. So you could have a CO sensor up there to basically say, when it hits a certain level, it actually stages the way the ventilation fans kick on. So you could actually stage it, you can modulate it however you wanted to do it. But the key thing here is that if you don't need 100% ventilation air into that space, there's no reason to provide that. As long as the environment is healthy for the people that are occupying and walking around that parking garage. So the goal is to be able to modulate the fan flow into that space, either through staging or through modulating the actual fan itself. Maybe you have a variable speed drive motor on that on the fan system. But it's tremendous energy savings in here. There are some exceptions. Obviously, there's exceptions with most of the requirements we've talked about in the energy code. Over the number of webinars we've done, but there's also exceptions to demand control ventilation too that we didn't talk about. So definitely it's worthwhile to dig into the code and see what those exceptions are, because they may apply to your design. So again, these are for fully enclosed parking garages, not where they're ventilated by trade winds. But in the instances where you do have those, then certainly this is a good way to save energy, as Howard talked about. Okay, so we've talked a little bit about sizing the equipment. We've talked about selecting to make sure that the equipment meets the minimum efficiency requirements. We've looked at controls on the systems. We've looked at controls on the ventilation fan systems. And again, I did mention earlier there's also kitchen exhaust fan requirements that we are not going to address today. But those are very similar to almost identical to what's in ASHRAE. There's also we haven't gotten into the code for lab hood exhaust. That they tried to get that in 2 cycles ago and it didn't get in. So there are still some differences between ASHRAE and the IECC, but the IECC covers most of what ASHRAE covers. Duct systems, the requirement that your 2006 requires you to seal duct systems and also to insulate the duct systems. The requirements really haven't changed. Any duct system that is essentially outside of conditioned space must be insulated. In this case, ducts in unconditioned space to an R6 insulation, ducts completely outside the building is to an R8. Located inside the building assembly, there's some requirements for that. Typically, ducts that are inside the building in conditioned space do not have to be insulated. There is a requirement in the code right now, and then there's a threshold that's put in there that essentially says if there's a greater than a 15-degree temperature difference between the ambient air that duct passes through and the airflow in that duct, then you should insulate the duct system. But if you look at the International Code Council interpretation in their commentary, they're essentially saying, ASHRAE does the same thing, basically saying that ducts in conditioned space do not have to be insulated. So it's a slightly different than the code language, but that's the way it's been interpreted. The only reason you may consider insulating that ductwork is for condensation reasons, if it is truly in conditioned space, and there's an issue with that. But other than that, conditioned space, you don't have to worry about insulating, but outside and in unconditioned space, one insulation level, and ducts outside, completely outside the building, another insulation level. So the other thing is, we are going to seal and insulate our ductwork, our piping, refrigerant piping. For your mechanical systems also has to be insulated, and so this particular table is set up based on fluid temperature. In the left-hand column, you have your fluid operating temperature range, and then a conductivity value for the insulation itself, and then the thickness of the insulation when you start looking at the far right columns. So if I had a small, let's say a 5-ton cooling system, for example, maybe I've got less than a 1-inch line running from that to the evaporator coil. I have to think about this. Yeah, it's my evaporator coil. So I'd have to put a 1/2 inch of insulation on your refrigerant line, and this is only for the line with the the requirements really haven't changed on what line you have to insulate. So if the fluid temperature is between 40 to 60 degrees in that particular line, then you have to put in on 1/2 inch of insulation. Now you'll notice as you look at the temperatures, there's no requirements for piping insulation on fluid temperatures between 105, but basically between 60 degrees Fahrenheit and 105 degrees Fahrenheit. That's really kind of considered unconditioned water. I'm not sure how prevalent water source heat pumps are in Hawaii. You're probably not worried about the certainly not worried about the heating size, but if you did want to use a water source heat pump, a lot of times the water temperature that flows that you're getting your cool from is probably going to be in the 60 to 105 degree temperature range, and those pipes typically aren't insulated. There's a lot of water source heat pumps being used here in the mainland, and so you see a lot of uninsulated piping that has fluid temperature that actually is between the 40 to 105 degree Fahrenheit range. So again, figure out your pipe size, figure out your fluid temperature, and then you would have to require comply with the thickness level. Now, if you have a large, let's say a hotel system where you have a large boiler, for example, for hot water requirements would be here too. You'd have to insulate your hot water lines. And you would go to this table. So for a boiler system for domestic hot water, you'd go ahead to this table, and if you're running your hot water, let's say between 105 to 140 degree temperature range, you would have to insulate those hot water lines. So this looks at piping insulation, looks at both cooling systems and also hot water systems in your particular climate. So here we also worry about boiler temperatures for heating too, and so we'd have to insulate. But from your standpoint, you're pretty much looking at just cooling and domestic hot water. So there are some exceptions, obviously. Direct buried piping for fluids greater than or less than or equal to 60 degrees Fahrenheit are exempted. Here's our piping range between 60 degrees and 105 degrees. Again, those are exempted. And then if your piping is internal to the HVAC system, you don't have to worry about insulating that, primarily because the piping and the efficiencies of an uninsulated pipe is already factored into the when they calculate out the efficiency for that particular piece of equipment. The other thing, piping for fluid not heated or cooled by electricity or fossil fuels. So theoretically, hot water piping that is heated by solar water would not be required to be insulated because solar would not be heated by electricity or fossil fuels. So solar piping would actually be exempt, but depending on your hot water needs, you may want to go ahead and insulate those pipes anyway. So you have to, again, this is a minimum code requirement. It doesn't say that you shouldn't do that. It just says you're not required to, but good design practice might dictate that you do that. So you have to look at what you're trying to accomplish for your design. Okay, so we've talked about kind of talked about the pieces of the mechanical system, and now the next big thing, and this is probably the biggest difference between the 2006 and 2015, is the requirement to commission mechanical systems. And this is not going to be for all mechanical systems or for all buildings. There's actually a threshold on here, and when we look at the threshold, we see in your case it would apply to buildings, total building equipment capacity, 480,000 BTUs per hour, cooling capacity or greater. So again, if I have a space in a strip shopping center, maybe a 5,000 or 6,000 square foot space or a 3,000 square foot space, and it's being handled by a couple of small air conditioning, packaged AC units on the roof, I'm not going to worry about this. But if I have a larger building with 480,000 BTU per hour cooling capacity, and that's going to, it does kick in the commissioning requirements, because what we're doing right now, we're getting a lot of our energy savings with mechanical controls. And we've kind of maxed out on equipment efficiency to an extent. We've sealed our duct systems up. We've put insulation on the distribution systems. We're putting it on, and so what the bulk of our savings right now are really going to be on controls to make sure that the systems are operated properly to match the loads. And so we need to make sure those controls are operating correctly. So the code will require you to submit a commissioning plan with the initial submittal of the project to the building department. And that commissioning plan, and there's no real requirements on format and things like that. If you're already doing commissioning and have something that works, it essentially says, here is how I am planning on commissioning the mechanical system. So the jurisdiction will get that. Once you have the commissioning plan, then as the system goes in, you make sure there's some set requirements in the code about what needs to be what needs to be tested, either functional testing or testing and balancing, that type of thing. But you have to go through a testing process of the mechanical system, and there are some functional performance testing requirements. Some of these will not apply to you. Obviously, the economizers, you are exempt from the economizer requirement in the code. But some of the other requirements for controls, obviously you need to make sure that they operate correctly, and there's some criteria in the code. And then once you've done this, you submit a preliminary commissioning report, and that preliminary commissioning report will essentially say, we did the testing, here's our findings, here's what we need to fix, here's what we need to make sure that it actually works. The preliminary commissioning report, the building department can require you to submit that to them to make sure you've done it. It's not, believe it's an option in the commissioning, but it definitely has to go to the building owner, because the building owner needs to make sure that they want to know that everything's actually working. So finalizing that, once a preliminary commissioning report is done, then the next thing is to actually go through and make sure that everything that's supposed to be working properly based on the design specifications on the plans and then the spec book actually work the way they're supposed to. You also need to make sure that all of the information is on the construction documents and also operation and maintenance manuals. That's all passed on to the building owner. That's already a requirement in your 2006 code that you pass on this information. This has just been moved to the commissioning requirements section of the code right now. So, and then you need to do a final commissioning report, near balancing report, and that final commissioning report goes to the building owner. And again, the jurisdiction they can require you to submit that to them too. Now, a lot of times the final commissioning isn't done until after certificate of occupancy. There's a lot of discussion in the code about how this should work, because from a jurisdictional standpoint, most jurisdictions do not want to hold up C of O because commissioning hasn't been completed. So this final commissioning report is actually can go to the building owner after C of O, just to get the people in the building and to make sure, but you do need to follow through and make sure that everything is working the way it's supposed to be working. So again, we've had Building Commissioning Association is very much behind this. We've tried to tweak the code this last time to actually put some teeth into who is supposed to be doing commissioning. Right now, the code requires a registered design professional to do the commissioning, and that has different meanings in different states. But the registered design professional right now is qualified to do commissioning underneath the provisions of this code. So you don't have to be SMACNA certified or building BCA certified, or I know there's other commissioning organizations out there, but there's no criteria that way. It just says registered design professional. So. Okay, so that's kind of completing the whole package on the mechanical side right now. What I want to do now is turn this over to Howard to talk about additional requirements you need to do in addition to the mechanical requirements. And Howard, why don't you dive into the additional efficiency package options?
With great pleasure. We mentioned before that this is a minimal code, and compliance should be pretty gosh darned easy. One thing we check for when we create or amend the codes from cycle to cycle is make sure that all the equipment specified is off the shelf and available at a reasonable cost. So to get additional savings, we have this provision where, in addition to all the minimal provisions you've complied with, there's one more to comply with, and we can see them on the next slide. And there we go. You only need to select one of these. We've got a lot of HVAC people in the audience today. That's a no-brainer. Just go up a couple of SEER, and incidentally, on the residential arena, the code specifies a 14 SEER for residences, and there is in town at a fairly reasonable price a residential unit with 32 SEER. So at the commercial level, I don't think there's anything that dramatic, but that would be pretty easy to comply with. And even easier to comply with would be the next provision, reduced lighting power density. I mentioned Moore's Law. LEDs are improving at an almost exponential rate. I just read about new diode in the factory that's rated at 200 lumens per watt. Just exceptional, and the LEDs are very, very easy to control also. So most systems now just have built-in controls there. So you have a tremendously easy time just achieving lower lighting power densities. And the next item I mentioned, enhanced lighting controls. There's already quite a bit of control built into the lighting system in this code, as we'll see tomorrow. So that's probably not a very viable option, especially considering how low the lighting power density already is. The lower the LPD, the higher the or the less payback there is for the lighting power or for controls. Next, on-site renewable energy. Of course, PVs come to mind. We have them all over Honolulu if Hawaiian Electric will allow us to install new ones. And this could also apply to solar water heating for commercial if you have a fairly low-rise apartment building with a large flat roof. You can dedicate a couple of parking lot sites or parking sites to large tanks that distribute throughout the apartment building. That would apply. And finally, high efficiency SWH. We think of SWH in Hawaii as solar water heating. In this case, it's service water heating. So you just up the efficiency there. And that does it for that, Eric.
Great. So Howard, I want to interject one thing on the more efficient HVAC. There have been complaints in other, in areas, actually it's primarily in areas with heating loads, that not all mechanical systems, you can't get mechanical systems that'll be, in this case, the code requires the efficiency to be 10% over 10% over the efficiency requirements that are in the main body of the code. And the way that this works is if you can't find equipment that meets the 10% over what you're planning on speccing, then you don't need to take this option. I mean, that's from a mechanical standpoint, this might be the easiest thing to do, but not all equipment actually can meet the threshold that's put into the options packages. And there, again, have been some issues with that because, but I think a lot of it's on the heating side, not the cooling side. So I just wanted to make you aware that when you start looking through the minimum efficiencies and you see 10% and your piece can't meet that, then you need to use another compliance option. But anyway, I just wanted to make sure that we talked about that a little bit. So that is about it. What I'd like to do now is to start taking some questions. We already got 2 questions in. Now again, if you have questions, like I said, we've already had 2 questions coming in. Feel free to email the questions to this email address, and we do like questions, as Howard said, makes it more interesting, and especially, there's a lot going on the mechanical side, so anything that you want to ask, go ahead and we'll see if we can answer it. But the first question I'm going to ask, and I think this is, if I'm interpreting this question correctly, is what happens in retail store like the Royal Hawaiian Shopping Mall, and I believe this probably is for the ventilation requirements that we talked about. That's the only thing I can think of that might, so the demand control ventilation. And I'll go ahead and take this one. So the one thing to remember is that this code is for new construction, and it's also for additions, alterations, and renovations for existing construction. And if I'm replacing an existing system on a retail store, okay, so retail space. So if I'm in the Royal Hawaiian Shopping Mall, for example, and unfortunately, Howard, you know what this, I'm not familiar with this, the Royal Hawaiian Shopping Mall, but I'm sure that you are.
I am very familiar with that, yeah.
Okay, so it might be very difficult for me to put well, actually, demand control ventilation, I could probably do it, but it might be very difficult for me to do a heat recovery vent, or not heat recovery, but the exhaust, losing my what I want to talk about here. Energy recovery ventilation system on that, because if you look at the thresholds that we've set on here, less than 25 people per 1,000 square feet, that means essentially you're going to be required to put energy recovery ventilation on a retail spaces. So if it's an existing building, existing space, there's and if you are changing out a cooling system, the way the code works is if you touch it, it has to comply with the code. So if I'm replacing a old packaged air conditioning system with a new packaged air conditioning system, theoretically, I guess I would need to comply with the energy recovery requirement for that particular system, because again, I'm taking the old one out and putting the new one in. If it's a repair, so I'm actually repairing it, or it's just a direct replacement, a lot of times that has been exempt. Especially, there's probably practical reasons why this may not work. We've had issues with economizers, for example, in the mainland, where a person takes an older system out and puts a new system in, and theoretically they have to comply with the economizer requirement and provide 100% outside air, and the system isn't set up to be able to do that. In that case, we actually have equipment efficiency requirements that you can fall back on to actually get out of that requirement. But in this case, you would really kind of need to look at this case by case to see if you needed to comply with the energy recovery ventilation requirement. So that would be the first thing. And also, and I'm actually, as I'm talking, I'm digging into the code right now, because there are some exceptions for energy recovery ventilation that might actually allow you to bypass this. And let me see if I can. So one thing, system serving spaces that are heated to less than 60 degrees Fahrenheit and are not cooled, that will not apply to you. Where more than 60% of the outdoor heating energy is provided by site recovery solar, we won't worry about heating because you're not on the heating. Cooling energy recovery, let's see, that won't apply to you. Systems requiring dehumidification that employ energy recovery in series with the cooling coil, or the largest source of air exhausted at a single location at the building exterior is less than 75% of the design outside or outdoor airflow rate. Systems expected to operate less than 20 hours per week, and systems exhausting toxic flammable paint or corrosive fumes or dust, and then commercial kitchen hoods used for collecting and removing grease vapors or smoke. So my recommendation would be to, again, take a look at the code language, take a look at the exceptions. I believe that ASHRAE actually, I think this is very similar as actually what's in 90.1. If it's still going to be an issue, then probably the ultimate call on this will be up to the building department on whether or not to grant a variance on this one. But that would be my recommendation right now. I do want to talk a little bit about existing buildings, because the code does cover existing buildings. And from a mechanical retrofit standpoint, again, I mentioned that whatever you touch, you have to comply with. So, but if all I'm doing is extending ductwork, for example, then I'm not required to bring up the entire system. I'm only required to make comply the new features to that building. So if I'm extending ductwork in an unconditioned space, I need to make sure my new duct is sealed and is also insulated, but I don't have to worry about bringing up the entire cooling system to comply with the code. So you really need to kind of look again at what the alteration is going to be for that particular space. So unfortunately, I don't have a great answer on this one, but it's really, you need to look at this on a case-by-case basis. So let's see, we have a couple of other questions. One's actually a resident or a commercial lighting. The other question, are there any exceptions to energy recovery requirements for HVAC systems, such as healthcare facilities? And that is a great question, because I know you need a significant amount of outside air coming into healthcare facilities. I mean, you could maybe, the only exception I could see on this would be systems exhausting toxic flammable paint or corrosive fumes or dust. If you could consider the exhaust falling under maybe toxic on that one. I'm not sure on that. That's something you'd also have to take a look at. Sometimes the International Mechanical Code, because there is an exemption on here where energy recovery systems are prohibited by the International Mechanical Code. Now, Howard, you have the Uniform Mechanical Code in Hawaii, right?
Yeah, that's correct. Yeah.
So there could be an exemption in the Uniform Mechanical Code that would allow you to exempt energy recovery ventilation. So that would probably be the first place I would take a look at to make sure that, if that's from a healthcare standpoint, something like that could actually fall underneath that, and it would make sense that it probably would. So again, consult the UMC on that one to see if you're exempted.
Yeah, and in any code, health and safety takes precedence over everything else. So if this is a health issue,
absolutely,
that's more important. Yeah,
absolutely. So the only other question that we have coming in, Howard, is actually it was on envelope from yesterday that they asked it today, and I'm going to go ahead and we have a little bit of time, so I'm going to go ahead and address this question because it's an interesting question. For metal buildings in Climate Zones 1, the 2006 code required roof insulation to be R19 plus R10 with R5.7 continuous insulation. So this is for metal buildings, essentially putting in a double layer of insulation. The 2009 code reduced the roof insulation to R19 with R5.7 continuous insulation. I noticed the 2015 code has been increased to R19 plus R11 liner system. When and why did the change to the 2009 code increase the roof insulation? And this is an interesting one because this actually came out of an ASHRAE subcommittee, a metal building ASHRAE subcommittee. And the members of the committee, and I don't know all the facts on that, reviewed all of the metal building requirements that were currently in the ASHRAE standard and decided when they looked at that actually the R19 plus the R11 liner system was probably about the best system to use in Climate Zone 1 for insulating the roof ceiling assembly, or for the roof assembly for metal buildings. And all of the provisions, actually, all of the roof assembly and wall assembly for metal buildings were modified in 2012, I believe, to address the new requirements from ASHRAE, and then modified slightly more in 2015 code. So one of the things to remember is that between the 2009 code and the 2015 code, in average nationally, is about roughly a 25% energy difference. And so so part of the modification was for metal buildings, and this seemed to be the most appropriate insulation system for metal building roof systems. And so ASHRAE adopted it, and then this actually came into the IECC from the ASHRAE requirements. And the metal building industry, from what I've understood, has supported this because I believe they supported this on the code change floor, or if they didn't support it, they were neutral on this. But anyway, most members of the metal building industry, I'm not sure if all members did, so I don't want to speak for all of them. But essentially, that's why the change actually happened in the most current provisions of the Commercial Energy Code. So, with that, Howard, that is the last question I have. So let me go ahead and show people how they can contact you for questions.
And again, I welcome questions. We've had questions from the previous seminars, and they've all been really good, and I've had fun answering them. And that brings us to another topic, namely, when the last webinar is through tomorrow, we will assemble all of the webinars, the full shoot and match, and put them on the Hawaii State Energy Office website. So they will be up there for perpetuity. And also, we are compiling the questions and adding them to our extant frequently asked questions site, again on the Energy Office website. And excuse me, something I didn't mention in the beginning is the perpetual question, when will IECC 2015 be adopted in Hawaii? That is an excellent question. I won't go into the details, but I'm hoping that perhaps the state and at least one or two of the counties will have adopted 2015 by the end of this year, and the remaining counties will adopt next year. But there is no reason whatsoever why you should not be using the 2015 already. And just to reiterate what Eric has said, the 2015 is somewhere around 32-33% more efficient than the 2006, so you are doing your clients a great favor by using the more 21st century type code. And that does it for me, Eric. Any parting words of wisdom?
No, I just appreciate everyone attending the webinar, and I look forward to seeing you tomorrow when we talk about the commercial provisions for the lighting systems in commercial buildings. So with that, Howard, I think we'll go ahead and say goodbye and meet up again tomorrow. So.
Yep. And in Hawaii, we say aloha. So, see you tomorrow.
All right. Thank you.